The scorching Texas sun blazed down on Fort Bliss in those final weeks of summer 1945. Within the sprawling military installation near El Paso, 118 German rocket engineers and scientists found themselves facing a reality beyond their wildest imagination. These were the minds that had created the terrifying V-2 rockets, the same weapons that had rained down on London mere months earlier. As prisoners who had become reluctant guests of American forces, they stood on the threshold of a revelation that would shatter everything they thought they knew about industrial capability. Among them was Dr. Werner von Braun, the brilliant yet controversial architect of Nazi Germany's most sophisticated weaponry. His arm remained tender from injuries sustained in a car crash while fleeing the advancing Soviet army. Like his colleagues, von Braun had faced an impossible choice in those final chaotic moments of the Third Reich. Years later, one engineer would remember their desperate calculation. "We despised the French. We lived in mortal terror of the Soviets. The British clearly lacked the resources to support us. That left only the Americans. Their surrender to American troops had seemed like a logical decision. After all, they had witnessed American bombing campaigns reduce German factories to rubble. They knew American soldiers. They understood American military equipment. Yet nothing in their experience had prepared them for what awaited: the sheer magnitude of production capacity, the overwhelming abundance of resources, the breathtaking organizational power of American industry. These sophisticated engineers would soon find themselves struggling to comprehend what they were witnessing. This story reveals how some of the world's most brilliant scientists encountered the industrial giant that had crushed the Axis powers. It captures the moment when technical excellence met raw, productive might, when European sophistication collided with American abundance, when the war's end revealed not just military triumph, but industrial dominance that would reshape the entire post-war era. The shock awaiting these German engineers becomes clear only when we understand the incredible transformation American industry had undergone during the war years. When German forces crossed into Poland in September 1939, America was still crawling out of the Great Depression. Military aircraft production that year barely reached 3,000 planes. The U.S. Army ranked 18th globally in size, smaller than Belgium's forces. American industry possessed tremendous power, certainly, but it focused primarily on civilian goods and export markets. By 1945, that landscape had been completely revolutionized. America had manufactured 300,000 aircraft throughout the conflict. American factories had generated 297,000 aircraft, 193,000 artillery pieces, 86,000 tanks, and over 2 million army trucks. The statistics were mind-boggling, but they revealed only a fraction of the complete picture. This transformation had begun before America even entered the fighting. In January 1939, President Franklin Roosevelt requested $300 million from Congress to acquire aircraft for the Army Air Corps. At that time, this request seemed extraordinarily ambitious. The entire Army Air Corps operated approximately 1,700 aircraft total. Roosevelt harbored a vision that stretched far beyond anyone's expectations. After Pearl Harbor's devastation, Roosevelt announced production targets that seemed almost impossible to achieve: 60,000 aircraft in 1942, 125,000 in 1943, 120,000 tanks during the same time frame, 55,000 anti-aircraft guns. When German leadership learned of these production goals, Adolf Hitler received assurance from his advisors that this was merely American propaganda. How could a nation that had produced fewer than 3,000 military aircraft in 1939 possibly manufacture such quantities? The answer lay in something uniquely American: the capacity to rapidly expand production through industrial innovation and pure organizational determination. American industry supplied nearly two-thirds of all Allied military equipment manufactured during the entire war. In just 4 years, American industrial production, already the world's largest, doubled completely. But success didn't come simply from constructing more factories. American industry reinvented itself in ways that would have seemed impossible just years before. Companies that had never touched military equipment suddenly found themselves converting to wartime production. The Mattituck Manufacturing Company in Waterbury, Connecticut, shifted from producing upholstery nails to manufacturing cartridge clips for Springfield rifles. They produced 3 million clips every week. American Brass Company manufactured over 2 billion pounds of brass during the conflict. Chase Brass and Copper produced more than 50 million cartridge cases and mortar shells. Over 1 billion small-caliber bullets. Eventually components for the atomic bomb itself. During wartime, 11,000 supermarkets opened across America. 2 million American women entered factory employment. Countless factories operated continuously, 24 hours daily, 7 days weekly. Workers frequently put in 12-hour shifts, 5 days each week, 10 hours on Saturday, 8 hours on Sunday. One worker in Mobile, Alabama, remembered those intense days. When it was so strong during the war, if you worked 12-hour days 5 days a week, 10 hours on Saturday, 8 hours on Sunday, you felt like you'd had a week off. The wartime economic boom was unprecedented in American history. In 1944, unemployment fell to just 1.2% of the civilian labor force, an all-time record low. About 10.5 million Americans who either couldn't have found jobs before the war or wouldn't have sought employment found themselves working. This included 3.25 million young people who reached working age after Pearl Harbor, plus 3.5 million women who joined the workforce for the first time. Between 1939 and 1944, America's gross national product expanded by 52%. Munitions production rocketed from virtually zero in 1939 to unprecedented heights. Industrial output tripled entirely. Amazingly, consumer spending actually increased during this period, unique among all nations fighting the war. The magnitude of this transformation becomes even more striking when compared to Germany's circumstances. While American industrial production was doubling, German industry struggled under mounting pressure. Germany confronted enormous governmental difficulties, supervisory problems, labor management conflicts, domestic political tensions that severely hampered their war effort. German factories suffered bombing attacks. Their workforce was being conscripted into military service. Supply lines stretched dangerously across an entire continent. Despite rationing and wartime limitations, American civilians lived better during the war than they had during the Depression years. Hollywood flourished as workers bought movie tickets rather than unavailable automobiles. Americans saved more money in 1943 and 1944 than ever before in history. Department store sales in November 1944 exceeded any previous month in any year. Even black markets for rationed goods thrived, a clear sign of underlying prosperity. But the true brilliance of American wartime production extended far beyond the raw numbers. It lay in the innovation, the process engineering, the organizational capabilities that made those numbers achievable. Historian David Kennedy observed that the United States innovated most characteristically and most effectively in plant layout, production organization, economies of scale, process engineering. American heavy bombers like the B-29 Superfortress were extraordinarily sophisticated weapons. They demanded innovations in bomb sights, radar systems, high-performance engines, aeronautical engineering, metallurgy, factory organization. These weren't merely products of American engineering brilliance. They were products of American industrial organization operating at peak efficiency. William Knudsen, the automotive industry executive who became chairman of the Office of Production Management, captured the essence of American industrial power perfectly. We won because we smothered the enemy in an avalanche of production, the like of which he had never seen nor dreamed possible. This was the industrial reality that German engineers were about to encounter directly. Men who had labored in some of the most advanced research facilities on Earth, who had designed rockets capable of reaching the edge of space, were about to discover that technological sophistication represented only part of the victory equation. The other part was something America had mastered beyond any other nation: the ability to transform innovation into production on an almost unimaginable scale. As the German scientists settled into their new accommodations at Fort Bliss in late 1945, they were entering a country that had not only won the war decisively, but had done so while becoming wealthier, more productive, more technologically advanced than when the conflict began. The United States emerged from the war not just physically unscathed, but economically strengthened by wartime industrial expansion. This placed America at both absolute and relative advantage over allies and enemies alike. The stage was perfectly set for one of the most remarkable cultural and technological exchanges in modern history. German scientific precision was about to encounter American industrial abundance head-on. The result would reshape both nations completely, ultimately helping launch humanity into the space age itself. But first, these captured engineers would need to overcome their initial shock. Their amazement at discovering just how powerful the American industrial machine had truly become. The summer heat of Texas paled in comparison to the intellectual and emotional intensity these men would experience as they began comprehending the true scope of American capabilities. They had designed some of the most advanced weapons on Earth. But they were about to learn that in America, advanced design was merely the starting point. The real power lay in transforming those designs into reality, on a scale that defied every assumption they had ever made about what was possible. As the first groups of German rocket scientists arrived at Fort Bliss between September 1945 and early 1946, they brought more than just their technical expertise. They carried their preconceptions about American industry with them. Many had spent the war years in underground facilities, working with severely limited resources, operating under increasingly desperate conditions. They had witnessed their V-2 rockets, constructed largely by slave labor, under horrific circumstances. They understood scarcity intimately. Rationing was second nature. The constant pressure of bombardment was familiar. What they couldn't understand was abundance. They couldn't grasp an industrial system that could produce not just what it needed, but what it wanted. They couldn't comprehend a country that had fought a global war on multiple fronts, while its civilian population lived better than they had during peacetime. They simply didn't understand America. The 300 freight car loads of V-2 components that reached White Sands by August 1945 represented the complete sum of German rocket technology. It was an impressive collection, certainly, the product of years of advanced research and development. But it was also finite, limited. The output of a nation under constant siege. In stark contrast, the Americans had already initiated preliminary rocket research at Fort Bliss during World War II itself. A comprehensive program for research and development of long-range ballistic missiles had begun in 1944, a collaboration between the Army Ordnance Department and scientists at the California Institute of Technology. The team had already successfully fired 17 private F missiles, between April 1st and 13th, 1945, at Hueco Range. This wasn't simply about capturing German technology. It was about integrating that knowledge into an already robust and expanding American research and development infrastructure. The German engineers were about to discover something crucial. They hadn't just been captured by the American military. They had been absorbed into an industrial and technological ecosystem that operated on principles they had never experienced before. It was a system that didn't just aim to match or exceed enemy capabilities. It aimed to overwhelm them through sheer productive capacity. As they began their work at Fort Bliss, helping Americans understand and improve upon V2 technology, these German scientists would gradually comprehend what their former enemies had accomplished. They would learn that the Americans hadn't just won the war through superior numbers of tanks and aircraft. They had won through superior organization, superior logistics, superior industrial innovation, superior abundance. The real education of these captured engineers was about to commence, and it would change not just their understanding of America, but their understanding of what industrial civilization could accomplish when organized for maximum production. The men who had designed Hitler's wonder weapons were about to discover what true industrial wonder actually looked like. But the full scope of that discovery still lay ahead. As 1945 turned to 1946, as more German families began arriving to join the scientists at Fort Bliss, the cultural and technological exchange that would reshape the post-war world was just beginning. The German engineers had witnessed American military might in action during the war. Now they were about to experience American industrial might during peacetime. And that experience would prove even more overwhelming than anything they had witnessed on any battlefield. The stage was perfectly set for revelations that would challenge everything these sophisticated European engineers thought they knew about production. Innovation, the very possibilities of industrial civilization itself. Their journey into the heart of American abundance was about to begin in earnest. The winter of 1946 delivered an unexpected shock to the German rocket team at Fort Bliss. It wasn't the Texas cold that left them absolutely stunned. Rather, their first organized tours of American industrial facilities. What they discovered would fundamentally challenge everything they thought they understood about production. Efficiency, the very nature of industrial civilization itself. Dr. Ernst Steinhoff, one of the leading electronics specialists on von Braun's team, later recalled his first visit to an American aircraft manufacturing plant with vivid detail. Walking through the sprawling factory floor, he watched workers assembling bombers on a production line that stretched farther than his eyes could see. In Germany, he would later reflect with amazement. We built our rockets almost by hand, each one a masterpiece of precision engineering. Here they were building aircraft like automobiles, dozens per day from a single facility. The scale was completely overwhelming, but it wasn't just about size alone. These German engineers, accustomed to working with severely limited materials and constant shortages, found themselves in facilities where abundance seemed almost casual. Raw materials flowed in steady, uninterrupted streams. Components were manufactured not just to meet immediate needs, but stockpiled for future production runs. Waste that would have been carefully recycled in wartime, Germany was simply discarded and replaced without a second thought. But perhaps most shocking was the incredible speed of innovation and adaptation. The Americans weren't just producing existing designs at massive scale, they were continuously improving, modifying, revolutionizing their production processes with breathtaking speed. What the Germans had achieved through years of careful research and development, American industry was accomplishing in mere months through rapid iteration and mass testing. The cultural shock extended far beyond mere numbers and statistics. German engineering had always prized precision above all else. Perfection was the goal. Theoretical elegance was paramount. The engineers at Peenemünde had spent years refining the V-2 design, creating what they considered a masterpiece of aerospace engineering. American industry operated on completely different principles. Good enough was often superior to perfect, especially if it could be produced quickly and in massive quantities. This philosophy initially bewildered the German scientists completely. They watched American engineers solve complex problems through brute force approaches that would have been considered wasteful or inelegant in Germany. If a component wasn't working perfectly, Americans often simply tried a dozen different variations simultaneously, testing them all in parallel. Rather than spending months perfecting a single design through theoretical analysis. The rocket team's integration into American research and development revealed another startling reality: the sheer depth of American scientific and technical resources. In Germany, the Peenemünde team had been among the elite. A small group of specialists working on the most advanced projects with extremely limited support. At Fort Bliss and White Sands, they discovered they were just one part of a vast network. Research facilities, universities, industrial laboratories, all working on overlapping and complementary projects simultaneously. Major James Hamill, who coordinated the German scientists' work, noted their constant amazement at the casual abundance of materials and equipment available. These men had spent the war years hoarding every piece of rare metal. Every precision instrument, he observed with interest. In America, they found laboratories better equipped than anything they had ever seen in Germany, and they were simply told to use whatever they needed without restriction. The V-2 launches at White Sands Proving Grounds between January 1946 and 1949 provided a direct comparison between German engineering excellence and American production capabilities. The Germans had brought approximately 100 V-2 rockets to America, representing years of production under increasingly difficult wartime conditions. American industry, meanwhile, was already working on multiple competing rocket designs simultaneously, producing components and test vehicles at a pace that left the German team absolutely astounded. But the real revelation came when the German scientists began to understand the broader context of American wartime production capabilities. They learned that the impressive aircraft factories they had visited were just a tiny fraction of total American industrial capacity. The United States had simultaneously built thousands of ships, millions of vehicles, countless weapon systems, entire new industries from scratch, while also supplying allies around the entire world. The Liberty Ships program exemplified this distinctly American approach to production perfectly. These vessels were designed not for elegance or longevity, but for speed of construction and massive scale production. American shipyards could build a Liberty ship in an average of just 42 days, with some completed in as little as 4 days and 15 hours. The Germans had never conceived of such rapid construction methods for complex machinery. The synthetic rubber industry provided another example that left the German chemists absolutely speechless. When Japan captured territories that supplied 90% of America's natural rubber, American industry responded by creating an entirely new synthetic rubber industry from complete scratch. Within just 3 years, the United States was producing more synthetic rubber than the entire world had previously produced natural rubber combined. This wasn't just industrial adaptation, it was complete industrial transformation on a scale the Germans had never imagined remotely possible. Dr. Hermann Oberth, the theoretical physicist who had inspired von Braun's early work, visited his former students at Fort Bliss in 1947. After touring American facilities extensively, He made an observation that captured the essence of what these German engineers were experiencing daily. In Europe, we create masterpieces, he noted thoughtfully. In America, you create systems that produce masterpieces by the thousands. The integration process wasn't without significant challenges and conflicts. Many German engineers struggled deeply with what they perceived as American casualness toward precision and traditional craftsmanship. They had been trained to optimize every single component, to achieve theoretical perfection, even at great cost in time and precious resources. American engineers seemed content with 90% solutions that could be implemented immediately and improved through continuous iteration. This fundamental difference in philosophy led to numerous conflicts during early collaboration efforts. German engineers would spend weeks perfecting a single component design, only to discover that American teams had already built and tested 3 different versions in exactly the same time period. The American approach often produced superior results through rapid experimentation than the German approach achieved through careful theoretical optimization. Gradually, however, many of the German scientists began to appreciate the tremendous power of the American system. They realized that perfect designs were meaningless if they couldn't be produced in sufficient quantities to matter. The V2, for all its remarkable technical sophistication, had been built in numbers measured in thousands. American production systems could build similar weapons in numbers measured in tens of thousands or hundreds of thousands. The economic foundation underlying American industrial might became increasingly clear to the German engineers as they spent more time in the country. Unlike Germany, which had been forced to choose between military production and civilian consumption, America had managed to increase both simultaneously during the entire war. The purchasing power of average Americans had actually increased during the conflict, providing a massive domestic market that sustained continued innovation and production. Dr. Kurt Debus, who would later become the first director of NASA's Kennedy Space Center, was particularly struck by the incredible depth of American technical education and research infrastructure. In Germany, advanced technical knowledge had been concentrated in just a few elite institutions and carefully guarded as state secrets. In America, he found hundreds of universities conducting relevant research, thousands of engineers working on similar problems, a culture that encouraged the rapid sharing of technical information. The contrast in management and organizational approaches was equally revealing to the German observers. German technical projects had been characterized by rigid hierarchies, careful allocation of extremely limited resources, detailed planning designed to avoid any waste whatsoever. American projects seemed almost chaotic by comparison. Multiple teams working on similar problems simultaneously, extensive parallel development efforts, a willingness to accept significant waste in exchange for speed and flexibility. Yet this apparent inefficiency consistently produced superior results. The Germans learned that redundancy and parallel development, while wasteful in pure theory, actually reduced overall project risk dramatically and accelerated innovation. If one approach failed completely, 3 others were already in active development. If one facility was destroyed, production could immediately shift to backup locations. The atomic bomb project provided the ultimate example of American industrial and scientific capabilities operating at full capacity. When the German scientists learned the complete details of the Manhattan Project, they were left virtually speechless with amazement. The scale of resources devoted to a single technical objective, the coordination between dozens of facilities across the entire country, the integration of university research with industrial production, the sheer audacity of the entire undertaking. It represented everything they had come to understand about American industrial might, concentrated into one massive, coordinated effort. Dr. Werner Heisenberg and other German nuclear physicists, when they learned of Hiroshima while detained in England under Operation Epsilon, had initially expressed complete disbelief. Some doubted the reports were even genuine. They had worked on nuclear fission themselves and understood the theoretical challenges intimately. What they hadn't understood was the American approach to overcoming those challenges through massive resource allocation and industrial-scale application. As the German rocket team's contracts at Fort Bliss neared their end in 1950, many faced a difficult choice: return to a completely devastated Germany, or accept permanent positions in America. The decision was complicated by their growing understanding of what they had truly experienced. They had not just been captured by a victorious army. They had been absorbed into an industrial civilization that operated on fundamentally different principles from anything they had ever known before. The move to Redstone Arsenal in Huntsville, Alabama, in April 1950 marked the beginning of an entirely new phase. Von Braun and his team were no longer just consultants helping Americans understand captured German technology. They were becoming integral parts of American research and development efforts. The knowledge transfer was no longer flowing in just one direction exclusively. At Redstone, the German engineers encountered yet another dimension of American industrial might that amazed them: the ability to scale up from research to production almost seamlessly. The Army Ballistic Missile Agency didn't just develop new weapons in isolation. It integrated design, testing, production, and deployment in ways that compressed timelines the Germans had thought completely impossible. The development of the Redstone missile exemplified this distinctly American approach perfectly. While maintaining the technical sophistication the German team valued highly, the project incorporated American production philosophy from the very beginning. Every component was designed not just for optimal performance, but for manufacturability at scale. Every process was planned not just for precision, but for scalability to mass production. By the mid-1950s, many of the German engineers had fully adapted to American industrial culture. They had learned to appreciate the tremendous power of rapid iteration, parallel development, massive resource allocation. More importantly, they had learned to combine their European emphasis on theoretical elegance with American emphasis on practical implementation. The launch of Sputnik in October 1957 provided dramatic validation of what these German engineers had learned about American capabilities over more than a decade. While the Soviet success initially shocked the American public, the German-American team at Redstone knew they could respond effectively and quickly. They had spent over a decade learning to harness American industrial might for advanced technology development. Explorer 1, launched just 4 months after Sputnik, demonstrated the fruits of this cultural and technical integration perfectly. The satellite was not just a product of German rocket expertise alone. It was a product of German expertise amplified by American industrial capabilities. The rocket that carried it into orbit had been designed using German knowledge, but built using American production methods and industrial capacity. Dr. Ernst Stuhlinger, reflecting on his 20-year journey from Peenemünde to NASA, captured the transformation that had occurred in all of them. "We came to America as prisoners," he observed thoughtfully, convinced that we understood the limits of industrial possibility. We learned that in America there are no limits, only choices about how quickly and at what scale you want to achieve your goals. The legacy of this encounter between German engineering precision and American industrial might extended far beyond just the space program. The hybrid approach that emerged, combining European theoretical sophistication with American production capabilities, became a model for technological development that influenced industries from aviation to electronics to computing. The German engineers who had arrived at Fort Bliss in 1945 believing they possessed the world's most advanced technology, had discovered something far more valuable. They had learned how advanced technology could be transformed into industrial reality on an unprecedented scale. They had witnessed the power of abundance over scarcity, of rapid iteration over perfectionist optimization, of industrial democracy over elite expertise. By the 1960s, as America prepared to land on the moon, the integration was completely finished. Former Nazi rocket engineers had become American space pioneers, not just through changing nationality, but through fundamentally changing their understanding of what industrial civilization could accomplish. They had learned to think not just about what was theoretically possible, but about what was practically achievable given sufficient resources and organizational will. The shock those German engineers experienced at Fort Bliss in 1946 had evolved into something far more profound, a new understanding of the relationship between knowledge and power, between innovation and production, between scientific achievement and industrial capacity. They had discovered that in America, the question was never whether something could be built, but only how quickly it could be built and at what scale. This revelation would reshape not just their own careers, but the trajectory of technological development for decades to come. The encounter between captured German engineers and American industrial might had produced something neither side could have achieved alone. A new model for turning scientific dreams into technological reality. And that model would carry humanity to the moon and beyond into the infinite frontier of space.